Eh? So that one, which no comment. And what is in French? Bonjour. Bonjour, morning. No? Who is Frankfurt? No Frankfurt right now.
लैपटॉप से कॉपी करनी
The laptop आ रहा है ना? क्यों? अच्छा. Okay, so see, last time I told you something which nobody has ever told me, right? And that was I don't know what was that. So I told you that splitting and coupling of signals are actually generally signals, and these general signals represent the neighboring proton, the influence. So if metal is split into a triplet because of CH2, it actually means three methods. One is seeing CH2 as alpha, adding into the magnetization. The other is saying beta, slightly negative B effect, it's slightly different down of you can see one up, one down, two probabilities, and you see this triplet. And this triplet is actually three methods. Three methods. The same method exists in three different forms. One watching neighbor in a different shape. And together they represent methods. So you call it splitting apart. Okay? Actually, they are genuine methods because they have three genuine ramifications, and they are watching their neighbor different. So the is that exactly is it? I'm just a method, but I exist in three different forms because my two neighbors are influencing. As a result of it, I have three different peaks, and these three different peaks cause splitting and to calculate J. That was a little finer point. Very exciting. So no magic. Remember, there is science is not magic. Science is always explainable. Science is always, it can be explained. We should have some kind of an explanation. And then I took you to that beautiful spectrum. And I said that this is theta TV, fully coupled theta TV spectrum of this small molecule monitor field, which is an alpha final. And that small molecule has 10 carbon, and these 10 carbons are all split because of attached protons. So CH3 appeared as a quartet, right? 4 different signals. CH2 appeared as a triplet, CH appeared as doublet, and quaternary carbon appeared as a single, right? So you see a spectrum like this. Fully coupled spectrum, explainable on the basis of n+1 rule. Right? N+1 rule is not a magic now. You can explain it, you understand that, right? So it's a beautiful concept which you now know. And I would like to ask you a question which can take you directly from Circle to Bhutan, closer to Islamabad. You know, see the name. He's saying there's such a pain to go to Islamabad. So, see the deal which you're watching here, 1%, 1.1%, 1/4 of magnet, a very poor magnet, is split because of the attached protons, right? On the other hand, when you see the proton NMR spectrum of ethanol, proton is coupled with carbon also. Why don't you see the splitting of protons? If we give you the answer, maybe you go to Bhutan directly. Okay. And then from Bhutan, you can even walk to Islamabad. There's only 600.
Okay, is carbon?
No, I don't want to decouple right now. At this stage, I just want to know. Carbon are split because of attached proton. Why protons are not split because of carbon?
Because activity what would look like it can be detected by 99% carbon universe.
So bringing him back from circle to Jaksha. That's beautiful. It goes to Bhutan. You know what he's trying to say?
That's what I
This is what you say? Okay, you both go to Bhutan. Or somewhere in between, like Rahim here. Okay, so what he's trying to say is beautiful concept. All C13, which you're trying to detect, attached with protons, and protons are NMR active, all of them, right? Okay. But all the protons, only 1% of those protons have a carbon 13 neighbor. You know, they are on carbon, they attach on carbon, but only 1% of those carbons are detectable. C13, the natural abundance of C13 is only 1%. So they all attach to carbon 12. Only 1% of the protons are attached to carbon 13. Clear? Not clear. Yeah? So, okay. So carbon 13, when you're detecting carbon 13, the protons which are attached to carbon 13 are all NMR active. Okay? Protons, when you're detecting protons, they all attach to carbon, but 99% of these carbons are carbon 12. Only 1% of them is carbon 13. As a result, you don't see proton splitted by carbon. There's only 1% of the carbon. If you have 100 carbons in your molecules, if you have 100 carbons in molecule, 99% of those carbons are carbon 12. Only 1% is carbon 13. Therefore, you don't see the splitting of protons because it's just very minute, very, very minute, which you don't really see. Understand? If you understand that concept, it's a good concept for you. Anyone can really ask you a question. Why carbon 13 spectrum is always when you have a fully coupled carbon 13, you see splitting. But when you have fully coupled proton spectrum, you don't see splitting of proton signal because of carbon. And you say, because of the natural abundance. Because they are not there. Carbon 13 is the only carbon which can split. And there is only 1%. Therefore, it's negligible. You don't say, forget it, your proton spectrum is neat and clean with no splitting, almost no splitting because of carbon 13, because only. Okay, so that was just a French information, very important information as a concept. Okay, so you see this, and you come across a problem that even for such a small molecule, you have a problem with interpretation. You know, it was a time I told you that the detecting carbon-13 was a major milestone in NMR spectroscopy. You know, carbon-13 is 6,400 but 6,400 times weaker than proton. 6,400 times weaker than proton is the cube of baromagnetic pressure, which is 64, 4 into 4 into 4, right? Which becomes 64, and then only 1%. So 6,400 times weaker carbon-13. All the development in first 30 years of NMR spectroscopy was to improve the sensitivity of this technique so you can detect carbon-13. All the development, big magnets, polarization transfer, pulse NMR spectroscopy, all was just for that. And the problem was that when you increase the sensitivity and you get a nice spectrum like this, you come across another problem of interpretation, which you will see. That you have all the information to the face of the earth, but it's difficult to interpret. All information is there, even for this small spectrum, but interpretation is different. And then people start working on how to improve the interpretation, capacity to interpret. And the next 30 years of NMR life was improving the interpretation. All two-dimensional NMR spectroscopy, three-dimensional, multi-dimensional NMR spectroscopy was a drive to be able to interpret the results, which is there in front of you, but you can't figure it out. Okay? Because the first solution was not really a very good solution, to be honest. A broadband proton NMR, proton frequency broadband decoupled spectrum gives you one signal for each carbon, but then you lose information. You lose information, you don't know which one is CH3, which one is CH2, which one is CH. You solve one problem, you create another problem. You solve the problem that you now see nice signals, chemical shift is so obvious, but you don't know multiplicity. You don't know which one is C13, which one is CH2, which one is CH, right? So solving interpretation problem, you come across the problem where you also have a problem because you cannot interpret that as well. You lose a very important piece of information about multiplicity. You know, when you construct any structure, you need all those information. It's a jigsaw puzzle. You need all these information. And then somebody said, why don't we just do something really different? And an absolutely brand new concept was developed. And the concept was a very simple one. And it was that CH3, CH2, CHs. CH3 will split into quartet. CH2 will split into CH will be and quartet carbon, right? And people said, why don't we just try to distinguish them by some kind of a phase difference? And a new experiment was developed, which is called attached proton test. Attached proton test. It's also called Getty-Spinnico or Spinnico Fourier transformation set. It's also called Getty-Spinnico. It's also called APT, attached proton test. And okay, so now envision that all your C13, CH2, CH2, CH3, CH2, CH2 are up, alpha pattern. Okay, you give a 90x pulse. You always need to give a 90 pulse because you need to bring it to X-ray plane, transfer magnetic. Your detector, your little beautiful detector is on Y, right? I made this beautiful eye, you remember? Okay, this was a piece of art. I don't know how many of you captured that. Don't show it to anyone. Okay, so this little detector is conventionally on Y. You need to bring all of them together and all CH3, CH2, CH polycarbon are the same place. When you give a 90x pulse, they call it coherent. But after some time, they fan out. They split. Because they're split, they are coupled with protons. So CH3 will split into 4, right? Some of them are moving faster, some of them are moving slower. Remember that the attached protons exist 3 up, 3 down, 2 up, 2 down, 1 up, 2 down, so many of these combination, 4 of them. And so they will split, fan out on the X5 plane because they have different couplings with attached protons. And remember, the frequency on Y, the Raman frequency on XY plane depends on B effective. All Raman frequencies depend on B effective. And any factor which affect B effective will affect Raman frequency. With attached proton, 3 attached proton are either adding into the magnetic field of C13 or opposing to the magnetic field, right? So Raman frequency of CH3 would not be the same as CH2. Raman frequency of CH would not be the same as CH2 and CH3. And Raman frequency of carbon 13 would not, quartic carbon would not be the same as. It's a beautiful concept. I really want you all to be awake, right? And intellectually, mentally, physically, emotionally, socially, I want you all there. Okay. Together, your presence is required, requested. Either you're here, but not socially. You feel so isolated. You okay? Are you sure? Okay, so now since you are here in all 5 dimensions of your presence, I want to invite you to CH3. When you give a 90 pulse, all are 90x pulse, they are on Y. Okay? When you let it evolve, you don't open the detector. You give it time, you know. They will split. CH3 will split into 4, right? CH2 will split into 3. CH will split into, and C will split into nothing. And this is your rotating frame. You are standing on it. Okay, so it's not moving anywhere. You just assume that. Now, after with the time delay, which is generally measured in J coupling, you see the quaternary carbon remain on Y plane. Y. So if you open the detector, you see a positive signal. Do you remember my face? I told you, right? This poor CH2, CH, which is split into 2, these 2 signals after this time will merge on negative Y. Right? This CH2, which is a triplet, will go all the way, complete the circle, and merge at positive Y. This CH3 will complete 1.5 circle and merge at negative Y. Okay? Because they have a different Raman frequency. They are running. So CH3, because of the presence of 3 neighboring protons, attached protons, is running faster it has completed 1.5 circle, right? So it is on negative one. CH2 has 2 attached protons, is running fast as well, but it's only complete 1 circle. CH has only one neighbor, it has completed half circle. And quaternary carbon remain there, because this is your rotating frame of reference. Now, if you turn on the detector, what will happen? Now, at that point, if you turn on the detector, you turn on detector now, because you have a complete control. Now you turn on the detector, CH3 will appear as a negative signal, CH2 appear as a positive signal, CH appear as a, and quadratic appear as, or you solve some of the problem. Now your spectrum, CH3 down, CH down, CH down, CH2 up, and quaternary up. You got some information. You got information which one is CH3 among all 4 types of carbon. Now you can group them together as 2, 2, 2 up, 2 down. And for that, you use attached proton as an anchor. It's called attached proton. So remember, when people were thinking, God, we have solved the problem, but at the same time we created a problem that we lost multiplicity, they came up with the solution. They came up with the solution called attached proton test. This is a beautiful experiment, in which you use differential Lambda frequencies of CH3 and CH2, and you turn on detector at a time where they are in different phases. As a result of it, you can distinguish at that time, in that spectrum, you cannot distinguish between CH3, CH2, CHs, and all are on the same phase. Now you can see CH3 and CH down, and CH2 and quaternary carbon up, right? So you solve partly that problem. The reason why I'm really showing you this is that exciting development all the way through. In proton NMR spectroscopy, people have been working all the way through, all the time. Even today, maybe 5,000 people are working to develop proton NMR into something else. Some are working on magnets, some are working on computers, some are working on pulse sequences and all that also. You like this? Do you appreciate it? Are you happy? Some of you don't feel happy. Some of you feel even sad. Some of you feel even depressed. Right? I don't see online participants, but I'm sure that the same proportion exists over there. Okay, so the online participants are present here in 4 dimensions, not in physically. But we are okay. So let me explain again. You see, these when you give a 90x pulse, they all are coherent. All are at the same time. Boom. You bring them on Y. Boom, right? And you don't expect them to be there forever. They have to split. And they have to go up also, right? So now CH2, CH, quaternary carbon, is based on the attached number of protons. Will have different energy levels, be effective, and Lambda frequency. Therefore, they will split and they will move on XY plane, right? And after some time, when you capture the picture, you turn on the detector, you see them in two different conditions. CH3, because of a faster alarm frequency, has completed 1.5 circle. CH2 has completed 1 circle, came back here. CH completed only half circle, and quadricarbon is at 5 anyway. So if you turn on the detector at this point and we start recording FID, this would be a negative phase. This would be a positive phase, negative phase, positive phase. Resulting frequency spectrum would have quadricarbon and CH2 up, and CH3 and CH down. The problem hasn't really, was not really solved fully. Well, ideally, you'd like to see CH3, CH2, quadricarbon all solved. You don't really want each one of them, because between CH3 and CHs, you still have a problem. Though I know how to integrate, because I know most of the CH3 will be based on hybridization, will be okay. I can make some partly sense. I also know that between CH2 and CH, quadricarbon, I know that quadricarbon would be downfield, right? So I can solve some of it, but not unambiguously, not so clearly, and for that the other experiments were designed. Okay, so if you appreciate it, I don't want to use understand, because I don't understand also. We just only understand partly. The best knowledge is when you lead with questions. Okay? The poor knowledge when you think you know. That is the worst thing you can think of. Right? So this is called the attached proton test, and this was I was showing. Time signal start from positive. Time signal start from negative. Time signal start from negative and positive. So you can see that this is your CH2. I don't know what. You know this. Yeah. This is what I was trying to last time explain. So this is the phase difference. So you use phase difference to eventually create a spectrum like this, in which CH2, CH3s and CHs down and quadricarbon up. They are decoupled spectrum because you have done decoupling. Okay. After splitting them, you have recombined them, right? So it appears as a singlet. And this was a problem for you. Remember, this was a problem because you don't know which one is CH3 and CH2. Here you know which one is CH3 and CH and CH2 and quadricarbon. You solve it, right? You partly solve it, not fully. You still have a problem. You still have a problem of explaining. Okay, so as I said that the first 30 years or so of NMR spectroscopy or so, the NMR spectroscopy, people are still working on sensitivity problems. A lot of DNPs are developed. Dynamic range spectroscopy is developed. New cryoprobes are developed. New whole range of different things are developed. But largely, the first 30 years, people were looking how to detect carbon-13. You know, all motivation was to detect carbon-13 because this was a domain of organic chemistry at that time. They wanted to detect carbon-13. You know, carbon is such a dear, close to our heart, loving element. We don't want to miss out. Proton is fine, we are happy with it, but proton doesn't really form a framework. Proton is attached on carbon. The actual framework of organic molecules, the carbon connect to carbon. So carbon has to be detected, and for that they have done lots of work to improve the sensitivity. Everything was done, such as, they have done big magnet was the easiest solution, because big magnet, big energy difference, big population difference, more lower frequency, better signals, whatever. So remember, I told you that NMR spectroscopy is inherently insensitive technique. And if you give me 4 reasons why it is insensitive, you move from Multan to Faisalabad. Okay. 4 reasons of why NMR spectroscopy is so insensitive as compared to UV, IR, mass spectrometry, advanced spectroscopy, X-ray crystallography, X-ray powder spectrum. So many of that. Shaida.
Larger wavelength.
So Shahida was sitting here for NMR spectroscopy 100 years ago when I was teaching. Close to that. Okay, so Professor Dr. Shahida. Professor Dr. Shahida said that something she said. Okay, who else? He said one, low population difference, because abundance also. Low population difference because of low population difference. Why low population difference? Because of the small energy difference, right? So if you have both states populated, and the difference is so minuscule and minute, is very insensitive, right? Second, natural abundance of most of the nuclei except proton, NMR active nuclei, it is so low, right? Third, gyromagnetic ratio, because they're also poor magnets. They're poor magnets. They're not so good magnets. Proton is an ultimate. It is here. It's like a godfather of all elements. Okay, but everything else is just underneath, very low magnet. Fourth, sample concentration. You see, okay, Amina, you can dissolve 1 kg of your sample in 0.5 ml. No? There is always a limitation. Even if you have 1 kg of your sample, pure compound, there's no use for you. You can only dissolve it up to a certain level when it doesn't become a supersaturated. Okay, so you have a limitation. This is small little 0.5 ml of solvent. It's 0.5 ml. 0.5 ml solvent you can dissolve only a bit. You can't dissolve forever and every quantity. So there's a limitation. But fourth reason. Superconducting magnets are the ways of improving the sensitivity. The fourth is that the signal is non-radiated. Yeah, because you don't really, relaxation is not RF radio frequency. RF never come from the system. You give a radio frequency, but radio frequency never come out. It converts into so many different types of energy. Only part of it is detected. So it becomes even more insensitive. So insensitivity is inherently a problem of NMR, But if it was not so useful, long time ago it has been buried into the scientific graveyard. Long time ago. People have buried that technique, like many techniques were buried in the graveyard. It was so useful that they say, what? 3 signals, 4 signals, every photon is coming differently. Integration is so nice, fitting of the signals also. So much information about the environment of every element which you have in its flexibility, that you can detect proton in the presence of carbon, carbon in the presence of and so on. So that is the reason why they have put so much effort. So, okay, so what was the natural solution? First was, okay, so these are, I keep asking you a question. The answer is yes, right? Good. You come back to Multan. Anyway, so the most obvious was high field magnet. More and more magnet. With the advent of superconducting magnets, it was so easy to develop large magnets. There's also a limitation, because you cannot really develop magnet to a very, very high power, because you cannot imagine the kind of electricity you need to pump in. If you develop 1,000 megahertz or 1.2, 1,200 megahertz NMR machine, and you think of developing a 2,000 megahertz NMR machine, think of what kind of electricity you need to pump in order to make that. It can burst everything out. So there is a limitation. Okay, but so far we already have commercially out available 1.2 gigahertz, 1,200 megahertz machine. Right? And remember, this is proton frequency or NMR spectrum. It is about 23 Tesla machine. 22 Tesla, 23 Tesla. And then cryoprobe. The probe which my colleagues have actually shown you, which is everything except magnet, everything is cryoprobe. Is probe. Except magnet, everything is in the cryoprobe, in the probe. Your detector coil, your radio frequency oscillator, your sample place, everything. This is your spectrometer, right? Sorry, this is your spectrometer. Except external magnetic field, everything is there. And they said, if we cool those electronics within the probe by gaseous helium, temperature is minus 21. Not liquid helium, gaseous helium. 4 Kelvin. I don't know how much in centigrade. If you cool your electronics in the probe with gaseous helium, when you cool it, remember that everything which is electronic perform well when it is cold. Because when you cool it, there is a dependency on temperature. Lower the temperature, higher the conductance, better signal. Lower resistance. You know this, right? That is the reason you can't really put your radio in Sahara Desert and expect you to have a signal. It will melt down. So we cool the cryoprobe. It's called cryoprobe. Cryo means cooling. Cryoprobe, and you get a better signal. This was also a sensitivity enhancement. Remember, this is a hardware method. This is a hardware method because you need to pay money, a lot of cash, a lot of money. And then, but these are expensive solutions. but then software solution. So the first was pulse NMR. We have already studied pulse NMR. Pulse NMR help us to have so many of spectrum recorded, and you have so many of spectra for the same compound, signal to noise ratio improved. Then there was a data manipulation. I don't know whether we have discussed that or not, but let me just take you through. Okay. This is FID. This is FID, right? Induction ticket. And this is the time domain signal. There are so many methods available, which is called mathematical processing. Nothing to do with hardware. This is how you manipulate that data. You know, I don't want to confuse you, but I want to tell you that this is the head of FID. Okay. Head of the FID. And this is tail of the FID. From head to tail, the content of information varies. You know, the information of your signal is all in FID. From our NMR lab, you get FIDs, and you process that into frequency. So people have developed mathematical equations to, you know, for instance, if they are interested in resolution, we multiply that with some factor. So the contribution of tail is increased. If you divide this with some factor, the contribution decrease. This is all number, right? So you can play with that. It's called apodization. Apodization. Okay. There's a whole science. People are trying to play with FID. You can create a pseudo FID. You know, if you don't have time, you just truncate here and create the tail by yourself. Expected tail. Simulation. So a lot of mathematical processes were developed which can improve the signal to noise ratio. I can at some point of time have a separate lecture on it, apodization. But let's move forward and go back to okay, so polarization transfer, that was the most important after pulse. This was the most important development in NMR spectroscopy. That has changed the face of NMR spectroscopy forever. And we will study that a bit more in length. But carbon-13 is about 6,400 times less sensitive. Gyromagnetic ratio of carbon-13 is 1/4 of photon. Photon is more sensitive, and carbon-13 is less sensitive. Carbon-13 signal will be very weak. The signal intensity depends on the population difference. Carbon-13 population difference would be very less as compared to photon. And if you can somehow transfer the polarization from sensitive nuclide from proton nucleus to carbon, you can enhance the signal. How can you do that? Okay. How can you do that? This is what you will study. But that was a wonderful concept which was developed. It's like Adil has to go to US. He has to show his background. This is probably performance. Okay. He's carbon-13. He has only 1,000 Egyptian pounds in the pound. Yeah, Mr. Pat. Huh? Mahmoud. Mahmoud is very rich. Apparently, he is rich. So he has like 1 million Egyptian pounds in his account. these proton, right? Because strong magnet, big population difference. Now, Adil wants this account temporarily look healthy. What do you do? And if he doesn't agree, then you just so that you cannot do that. Mahmoud is kind enough that you would need no violence to transfer current. Okay, so Mahmoud will transfer proton, will transfer polarization to carbon. And Adil, as a carbon or nitrogen, will look healthy. His bank statement look healthy. Okay, he gets the American visa, never return money. But I'm sure that he will do that. So this is a temporary polarization transfer or population transfer from more sensitive nuclei to less sensitive. Very often from proton to carbon-13, proton to nitrogen. You know, in molecular structural biology, they play with nitrogen, so they are more interested in nitrogen, and nitrogen also insensitive nuclei. Paramagnetic ratio of nitrogen is also very less, and natural abundance of nitrogen is even less than carbon. It's only 0.26 or 46%. So, how would you do that? How would you transfer the population or polarization from less sensitive nuclei, no, more sensitive nuclei to less sensitive nuclei? There was a polarization transfer. A lot of people have worked on it. And that was all this depth, inept, synept, all these experiment, distortionless enhancement, the polarization transfer, inept like insensitive nuclei enhancement by polarization transfer, CNAP, selective enhancement of insensitive nuclei by polarization. And so many of these experiments were designed in which temporarily the polarization proton is transferred to carbon-13, and carbon-13 so looks signal look bigger, right? So this is software way of improving the sensitivity. We'll study that. We'll spend a whole lecture on it. And then, of course, inverse polarization transfer and nuclear overall effect. These are ways of, and then, of course, there are methods in which you can add certain chemicals in your NMR tube. And that helps in increasing the sensitivity because these chemicals are paramagnetic and can help to improve the FID, quickly FID. I'm watching watch, not because I want to run away, because I have another lecture. And that is in Uganda. Who's from Uganda? Okay, so you can attend that lecture if you wish to. You can be with him. Okay, in McCreary University. Okay, and your teacher Jen, convey her regard to you. Amen. Okay, and she said that you are working fine. I think you have created a good impression. I said I'll give you feedback after class. Okay, so these are the some of the methods to improve the sensitivity, right? There may be other methods like that. And if you go to high field NMR machines, now this is outdated slide to be honest, because this is what I saw in 2009 when I went to Lyon, France. I went to Lyon, France, and my very old friend, she was working in natural product chemistry. And in December 2009, this machine was installed. This was the first 1000 megahertz machine at that time.
Why the size?
Because, you know, if you have a large magnet, you need to have more helium and more nitrogen. And you need to actually go stairs up. Or you make a ditch. You put it down there. But, you know, the best method is this one. Which you always have a problem of water seepage or so many other things also. But this is mechanically stable, and this is a machine. So this person is not doing anything except putting the sample on it. The sample goes here. The probe is here, right here. Probe is inserted from the bottom. Probe is here. And this is 23 Tesla machine. And now 1.2 hertz, which is about 25.8 Tesla machine. Larger and larger, but you know, can't measure the expensive solutions. This is literally millions and millions of dollars. I don't really think that anyone in the Asian subcontinent, except China and Japan, or maybe Korea, would have 1.2 gigahertz machine. One we have is about 800, but there's a cryo-800, which is about 900. Okay, so okay, that's a good question. How long it take? Okay, so if you're planning to buy a 300 megahertz machine, that is available off the shelf. There are many of these 300 megahertz machines because the sale is large. If you pay the money, then you will get it maybe like 2 months time because they have to do some kind of in-house installation, de-installation, send it to you. The NMR machine doesn't really come as a whole; it comes in half. You need to sample it, and then somebody will come sample it, make the magnet superconducting, quench it, install it, and then go full commission. But if you are ordering 800 or 1000, it's not available off the shelf. They would install it. They will make it for you. And they will make it. Of course, there's some companies already ready, such as this Diva. Diva is actually Surahi. It's Surahi, no? But then, you know, magnets has to be developed and computers and a lot of things has to be, and they will say, okay, we'll get it after 1 year because it takes so long to develop that. So, or 6 months. 1.2 gigahertz, they say, okay, give us the money, the thing will be you. Okay. So, this is the kind of this is what we will study on Monday. I'm here, right here, coming from Islamabad just to teach you. To teach myself, sorry. I can't teach you, I can just teach myself, I can learn from myself. But in between, I'll go and give lecture in Uganda, Kampala, a beautiful Uganda. You know, sometimes I'm really thinking of buying a house along the Victoria Lake, along Anthony. It's possible? Can you do that for me? I don't have money. So you will have some kind of interpretation and
so we'll be discussing about the small molecule, but even then it's like not very small. And I would like you guys to involve in the interpretation. Okay, so I will show you the spectra. And now you know it's the part of Levon class. Okay, so here the proton NMR spectra is. And what is the frequency of proton NMR it was recorded? Huh? Now you know the structure. Now you have to interpret. Huh? 600 megahertz. So here it is written 600 SF01 whenever you ever would like to. So this is 600 megahertz. And how many number of scans are there? Hmm? 8. Good. So you have 8 number of scans. NS is 8. And what is DS? Dummy scans. So dummy scans, here it is 0. But usually when we have a bit longer NMR experiment, so we would like to have some dummy scans, like 8 or 16 or 32. And these, longer experiments, things like that actually goes for days. And specifically when we are running 3D NMR, so we would have sometimes 64 and 128 dummy scans. So dummy scans are the why we need to have dummy scans. Dummy scans are the part of your experiments, but whenever the NMR spectrometer starts giving pulses, then there is a slight change in the temperature, right? And due to the variation in temperature, you are going to record the experiment for a longer period of time, maybe 2 days or 3 days or whatever, and then it may change the chemical shift because chemical shifts depends on temperature as well. So when we would like to have a stable temperature before it starts recording, so recorder is not on, experiments ongoing, but recorder is not on, and that is called dummy scan. And most often, for short experiments like proton NMR, it's recommended to have at least 2 or 4 dummy scans. But if it is not there, even that is okay. For these are very short experiments. And what is the pulse program here that has been used? All right, good. So ZG30 is a pulse program. It is, and usually in NMR experiment, ZG is 0 go. Then we start the NMR experiment. So ZG30 is the name of the proton NMR experiment. There are thousands of NMR experiments, but ZG30 is for proton NMR. So these are the important things. And then which nuclei at one channel. So there are in our spectrometers, we usually have minimum 2 or 3 channels. So I would say like at least 3 channels are there. One is deuterium channel, one is proton and sugar. The deuterium need to be there because we are using deuterated solvent for lock and everything. So deuterium channel is must. Proton channel and C13 channel. In some probes, we can only have the proton channel, but there is no use. We are not using proton NMR only. So we usually have the 3 channels. So here the F1 channel, which actually the nuclei one, which we are going to record is proton NMR, right? And P1, what is P1? Yeah, 7.4 microsecond, but what is that? This is 90-degree pulse. You know, that sir was talking about, that the 90-degree pulse that you have to give when your M naught is on the axis, and then you give a 90-degree pulse, and that comes here. So this P1
is the
is,
after this pulse,
huh?
is the time.
Time?
You want to know what you want, T1 time.
You said it is the
No, no,
pulse.
no, it's the pulse duration.
What is the
P1.
number now?
What? How did you get this number?
What is the meaning?
What is the meaning? Is the duration of 90-degree pulse?
Time. Duration is the
Yeah, exactly.
time after this 90 pulse.
No, it's just the time for the 90-degree pulse.
From the sea to
XY plane.
time is pretty much.
Yeah. Okay. And then PL1 is the power that is being used to bring the magnetization vector from z-axis to xy plane, and it is called PL1 is in dB or watt in there. And so this is the PLW, PL1W. So this power in dB, decibel, and the same power in watt. Okay. And then you have, these are the important things and that you should know. And the window function that you use here, so that is EM, and you can try many other window functions as well. And then SF is the frequency of the spectrometer. Okay, so the end solvent. Solvent is acetone, so it's deuterated acetone, always, you know, whatever written here. So you always use deuterated solvent. But sometimes, like when we are doing experiments of biological macromolecules, so we use water, different buffer chemicals which are in water, and we use 5% B2 only for long. And the reason behind it, because there are many exchangeable protons, like amide protons, we were talking about protein. So amide protons are exchangeable, right? And we do not want, as Dr. Eva said, biological, those people who are working in biology and macromolecular NMR, they do not want to use the information of nitrogen. So we do not want that if it is exchanged, then we cannot, because this is an inverse NMR. And what is inverse NMR? That's what we are using. So other than this, we usually use deuterated solvents. And these are the acquisition time and the spectral rate and the receiver gain. So all these is to optimize before you start this. Okay, so now another important thing, the spectral width that you have to define all this, right? And here you define the spectral width, I think it's like from -1 to 15 ppm. But that spectral width you have to define. Okay, it doesn't take it automatically. You have to write the spectral width when you are doing NMR experiment by yourself. And then you have to select the middle point as well. Anyway, so here in this spectrum, so here this part is called upfield chemical shifts and the downfield. And of course, yeah.
What is upfield and downfield? They have sessions.
Okay.
When we put the downfield is the high number of
Okay, so upfield, it means those protons which are surrounded by the number of electrons that actually protect them from the influence of the numbers. Okay, so that actually let the proton to resonate in, because it doesn't require that much energy to resonate. So that is why it actually resonates in the upfield region, which is this one. Okay, when it is when you have some some electrons that are actually, for example, if you are talking about some panel rings, right? That the pi electron in the ring actually are opposing, are aligned to the magnetic field. That it means that actually giving more effect on the nuclei, and that is why it has to move and appear in the downfield region. Okay.
We have this two words. I means something more. And now something go. Where is this here? I, the number it should be big numbers. Or something is high. But no, the high is
We will discuss it later. Let's move forward. Okay. All right. So here, looking at the chemical shift, we have from 7.8. Now, I would like all of you to calculate the J value of this proton. Calculate the J value. Good. You don't know? Okay, so when you just, Dr. Iqbal in the last class discussed the couplings, right? So we need to know the coupling constant. And to calculate the coupling constant, we would like to subtract these two values, right? And whatever the value comes, it will come in ppm. That's very, very small. So we need to multiply with the frequency of the spectrometer. And then we will get answer in hertz, right? Good. On your notebook. So you need to subtract 7. As a matter of fact, you may not get it correct because here it's 7.84. To get accurate value in proton NMR, you should have the 3 digits. You must have 3 digits after point. Okay, so 6. All right. So if you have, sometimes these are techniques. So whenever you get some kind of a spectra, you go and ask them, you should have 3 digits after the point. Only then you can calculate the correct J value. Okay, so this is the problem in this spectrum. Anyway, so here, this seems to be doublet. Okay, and then 7.0 as a singlet. And what about B? Doublet of a doublet, double doublet, right? So I would like you to calculate the J value of this double doublet. Yeah, you need to, whenever this kind of situation appears, then you need to calculate the J value of 1, 2 and 1, 3. Okay, so here means 1, 3, 6.57 minus 6.56. This is 1, 2, 1 and 2. And 1 3 means 6.57 minus 6.55, 1 and 2. Okay, so this is the J value you need to calculate. Yeah?
Except with
6?
with
Yeah, 6 in charge. Okay. What? I couldn't get you. What you were-
How we calculate parts of the column, start from the first one.
I'm not getting your question.
You say again to achieve values for the doublet of the.
They are two given. Why they are two given? Oh, okay. So now you have actually discussed the Pascal triangle and plus one rule. But here, this is, we are not, the protons are not following and plus one rule. When it is, that doesn't doublet of a doublet. It means you have a doublet here. Okay. And then you have doublet. Okay, doublet of a doublet. And sometimes it's okay, so it means this is also doublet of a doublet. So in whatever the way, need to calculate these two J values and these three J values. 1, 2, and 1, 3. And when you calculate 1, 2 or 1, 3, you get the information of this distance and these. So that is why, and that would be the same for the other part as well. So, but this is not following n plus 1 rule. It's little bit more complicated.
This could be explained how to calculate J value of doublet of doublet.
I just did. You need to subtract 6.57 minus 6.56 and multiply 600 because of the spectrometer frequency. So 1, 2 coupling, okay? And then 1, 3. 1 means 1, this, and third number is this. 6.57 minus 6.55 multiply by 600. So 1, 2 and 1, 3 coupling. Okay, what is, everyone got it? What's the answer? 6 and 12, good. Alright, so now I would like to calculate the doublet. So calculate the J value of this bit. Yeah, that is why I told you. Because at least you should have 3 digits here. So this is the problem in this spectrum. I think next time, Humera, we will get the correct spectra with 3 digits value because there are very minor splits, right? And that could you only calculate when you have 3 digits value. And for proton NMR and for C13, you just need one here, just 7.8, for example. And you do not need 2 or 3. And you do not have to mention this in your thesis and research articles. For proton, no? What? What is it? Yeah, we cannot calculate right now. Yeah, next time in next class on Monday, this is correct. Means like correct, and this is also correct with the 3 digits. And this similar, we cannot do it because the splitting is very teeny tiny. And this one we can calculate definitely. What is the J value there? 6. So looking at this, we have some so here you could see you have protons that are parallel to each other, right? So you should get you might get or might not get because it's a para coupling, very tiny coupling. Sometimes it's very, very rare to get the para coupling. Usually you get two single protons, right? And then here, this proton should appear as a, why is English? Meta coupling, good. So it should appear as a doublet because of the meta proton, right? So this is meta couple, and meta coupling, why we need to calculate the J value. So when the two protons are meta to each other, then they usually have J value between 0.8 to 2 hertz. Okay, and when the protons are ortho to each other, then they have the J value from 6 to 8 hertz. So whenever you get the less J value, then you know that this is meta couple and it should appear as a doublet. Why doublet? Because of presence of this meta proton. It should split into doublet. And what about this? This doublet. Because of the presence of ortho proton besides this. And the J coupling of this proton would be between 6 to 8, 7 to 8 or 6 to 8. And this proton should appear as a doublet of a doublet. Why doublet of a doublet? Because one time it is split because of the ortho proton, and the second time it is split because of the meta coupling. And this should appear as a singlet. So we should have here there are double doublet. How many protons we are expecting? 1, 2, 3, 4, 5, 6. Right? 6 protons. Huh?
And one for OH.
Yeah, OH depends. You know, there the presence. That's an OH mostly depends on the solvent. Okay, which solvent you are using. If you are using methanol, then probably will not observe any proton. So it depends. Usually, when we are solving the structure, unless we are doing and studying some kind of hydrogen bond, we do not assign proton of hydroxyl. Okay, so we were expecting 6 protons, right? And how many have raised? Huh? 1, 2, 3, 4, 5, 6. So these are 6 protons. Now this you exactly know. It's a doublet of a doublet, right? And when we look at the ring, so this proton was doublet of a doublet, right? Only because of the splitting pattern. And here it is a singlet. And this one is quite broad coupling. So it shows that ortho coupling, right? It cannot be a meta coupling. Meta coupling are small coupling, and you got this value like 6. But we will check it again on Monday when with the 3-digit value. So this is ortho coupled proton. And when we look at here, so this is the ortho coupled proton. Now we know ortho coupled and doublet and doublet of a doublet. And then we have a singlet here, 7 and other 3 are, but we do not assign them right now because we do not have the exact J value. Once we have the J value, we can easily assign all protons. Okay, so we will discuss this on Monday, the further assignment. Okay, so here, that's very interesting, but you know, in this when we look at the structure of these protons, so how many carbons are there? Looking at the structure of this molecule, how many carbons are there? 15. 15 carbons. And how many quaternaries are there? Can check again. So 1, 2, 3, 4, 5, 6, 7, 8, 9 quaternaries are there. Okay. And which one would appear the most downfield? Okay. And so among the all quaternary carbons, we should have one most downfield one that we will assign to carbon. And okay, so here one important thing that I would like to tell you. Okay, we have quaternaries, and how many methane are there? CH, methane. 6, right? Any CH2 here? No. Any CH2 here? No. Okay. So in when we look at the broadband spectrum, so in the broadband spectrum we got all carbon, all C, CH, CH2, CH3, all are there. Now again, we were discussing that there is a problem. This is decoupled spectrum, right? So no coupling is there. We are just a bit confused where to assign and which one to assign what, right? And this is solvent. Let's ignore it, okay? And others are the chemical. So we have depth 135. In depth 135 spectrum, all CH2s are hanging down, but there is no CH. Okay, and here in depth 135 and depth 90, only those carbons that have proton attached to it will appear. No quaternary carbon. Okay, so if you subtract this chemical shift, make a list, not subtract, like identify, okay, and compare. So, and those carbon which are not appear here and here. This is depth 135 and depth 90. So that means that are quaternary carbons, right? Because only broadband have the quaternary carbon. If you compare the chemical shift of broadband with depth, that is distortion-less enhancement by polarization transfer. Depth 135 and depth 90, then you can identify quaternary carbons. And here we look. So all these are not there. So it means they're quaternary, right? Okay, so and depth 135. In depth 135, we have CH2 downward and CH3 upward, right? And CH is also. So all carbon that has proton. So downward is CH2, up CH3 and CH are in depth 135. In this molecule, we do not have any CH3 and CH2, right? And in depth 90, we have only CHs, only CH. Okay, no CH2, no CH3, And so if we compare these two, these are CHF, the hanging downward are CH2, what remaining are CH3. Okay, so the information that we lost in the decoupled broadband spectrum, as Dr. Iqbal showed you, the coupled spectrum of carbon-13, and when we decouple it, and you remember, one of you told sir, that you can decouple on when you have the proton frequency very high. They are just moving like a fan. So they just decouple. So we lost the information of coupling here. But with depth NMR, we can get this information back, because depth 90 gives the information of CH only. And when we compare depth 90 with depth 135, then we can get the information of CH, CH2 and CH3. Since this molecule doesn't have any CH3 and CH2, that's why we do not have. Otherwise, CH2 are hanging downward. All hanging downward are CH2. And if we compare the remaining spectrum, remaining signals with depth 90, then we can get the information of CH3, right? So, and when we compare these two with broadband, we got the information of formyl carbon C. So now the problem on the information that we lost earlier, we can get from these two additional NMR experiments. Okay, and all are decoupled spectrum, right? These are carbon chemical shift only. They are not coupled. You can see each one is a singlet, right? And so it's a decoupled NMR spectrum. All these three. And polarization transfer, like the way Dr. Iqbal was explaining today, is part of each NMR experiment now. Okay, so it's just getting the magnetization or polarization from proton and then enhances it. Maybe Dr. Iqbal in next lecture he can explain further about the polarization transfer. Okay, do you understand this? Okay, so I think I'll stop here. Yeah. When we can.
When carbon having carbon I have had an experience very long.
Yeah.
Very know that there are two carbon.
Okay, no, this is not correct. You know, this is absolutely not correct. The intensity of carbon-13, it will not reflect anything. Sometimes, and Dr. Iqbal will teach you the reason when we will come to that point. We cannot get the number of protons from the intensity at all. Okay, this is, whoever tell you this is completely wrong. But definitely you may have some prediction. Yeah, like these are small, maybe it's a quaternaries, right? Because it doesn't have proton attached to it, no polarization transfer, because all these experiments has the polarization transfer. So they can get the information or polarization from the proton attached to it. So that maybe, otherwise CH, CH2, CH3, they have almost a similar, in different molecules, here's different. So you cannot exactly say that this is CH2 or this is CH3 based on the intensity. Intensity doesn't mean anything in that decoupled C13 NMR. at all. Maybe you can guess based on one molecule, but your hypothesis will completely fail to the other sort of molecule. There is no such rule.
And we now have a peak representing 2,000.
Yes, you can have that. For example, in a situation, and that's very common. If we take the example of lemon, this is ring A of lemon, right? Just consider this wall group, another panel line. So, for example, you have CH2 here, CH2 here, right? So these two are exactly same if their environment is like here is the proton, here is the proton, so they will appear at the same. Okay, so you can have two carbons which are magnetically equivalent, and that will appear at one chemical shift. Otherwise, and that's very rare. Otherwise, all carbon, if they're little bit changed, because these values again, you should have the 3 digits, but you should not report 3 digits for C13. You should not write. But when you have 3 digits, you exactly, and there is, for example, another carbonyl which has 183.387. Even that much difference, you can see the 2 signals. And the reason behind it is starting from 0 to 220 scale. And in proton, you have that scale. So, the information is there, just overlap. But here, the scale is bigger, so all these are separate. But you can have those carbons that are magnetically equivalent, you can have at the exactly same temperature. All right. So any other question? Yeah.
Between big 5 and actually working test.
Okay, in attached, and this is the attached proton test was the first generation of earlier. We can still run attached proton test, but this one is more sensitive. It's more advanced pulse sequence. Okay, and then the attached proton test. And in attached proton test, you've seen that you can get the information of, all these that experiments were also run only to get the information of the neighboring protons, like it's CH3, CH2, or C, whatever, which type of the signals are. Attached proton also gives the same, and this is the next generation, that was for how long, maybe a decade or so, people were doing attached proton test. Then this sequence was developed, and now people mostly report distortion as it's more sensitive because of polarization transfer and other things. There are pulse sequence that has been invented, or people write their own pulse sequence and run their NMR experiments. So that you can always do. So this is the same information, but it's a next greatest, advanced, more sensitive. And similarly, when I was a student, usually do HMQs. Okay. And that is now the same information, which carbon and proton come. That we got the information. And that is 2D experiments. Now, most of us we are doing HSQC. Okay, HMQC is heteronuclear, two nuclei, multiple quantum coherence, and HSQC, heteronuclear single quantum coherence. The pulse sequence is being changed. Information is the same, and that's more sensitive. So that's why we are using that one. You know, it always with the passage of time, new pulse sequence is being invented that has, you know, NMR has a big problem of insensitivity. And so that's why people are working to get better pulse sequence, to get better sensitivity. Good question. Any other question? All right, so we'll discuss the remaining on Monday, inshallah. Okay? Yeah. What? Okay.
Copy the